In this video, we will discuss the following topics: the VisSim unit delay, modeling a pulse counter, setting the unit delay initial condition, and modeling a discrete integrator. The VisSim unit delay block, located in the Blocks Time Delay menu, applies a zero-order hold to a signal with either a fixed or varying sample time. The unit delay block accepts two inputs: a Boolean pulse input labeled B used to trigger the delay, and a signal or sequence input labeled X. Let's simulate the application of a unit delay to a ramp input signal. From the Blocks Signal Producer menu, we'll select a unit ramp and attach it to the unit delay signal input. We'll trigger the unit delay with a pulse train block located under the Blocks Signal Producer menu and attach it to the Boolean input. Right-clicking the pulse train to view its properties, we'll set the time between samples to 0.1 seconds. From the Blocks Signal Consumer menu, a plot block is connected to the unit delay output and the unit ramp signal. Under the System Properties menu, we'll set the simulation to run for 1 second with a time step of 0.001 seconds. Clicking Go produces the two time histories: the ramp input in blue and the unit delay output in red. Note the 0.1 second delay and hold behavior after the initial condition has occurred. Now we'll apply feedback to our unit delay block to model a pulse counter. A summing junction which adds 1 to the unit delay output is used to create the unit delay signal input. We'll use a pulse train to generate the pulses to be counted. The pulse train is applied to the unit delay Boolean input, and the time between pulses is set to 0.2 seconds. From the Blocks Signal Consumer menu, two plot blocks are placed on the screen. One records the pulse signal, the other records the pulse count. Under the System Properties menu, we'll set the simulation to run for 1 second with a time step of 0.001 seconds. Clicking Go produces the two time histories. In the top plot, we see that 6 pulses have occurred. In the bottom plot, we see our pulse counter has only counted to 5 pulses. This is because the initial condition of the unit delay is set to begin at 0. Let's set it to 1 and rerun the simulation. Now with the unit delay initial condition set to 1, we see the pulse counter has counted correctly to 6 pulses. Most digital controllers execute at 1 or more fixed update times. It is good practice to create a unit delay compound block whose update time can be controlled by a single global variable. We'll name our unit delay compound block UD. It will consist of a unit delay triggered by a pulse train with the time between samples set by a global variable named update time 1. We will use our UD block to model a backwards rectangular discrete integrator operating at a 0.01 second update time. Our test signal U will be a 10 pi radian per second or 5 Hz unity amplitude sinusoid. We'll create the discrete integrator by multiplying the test signal by update time 1, adding this to the previous integration value, which is the UD block output, and then applying the sum to the UD block input. From the block signal consumer menu, a plot block is connected to the digital integrator output. Under the System Properties menu, we'll set the simulation to run for 1 second with a time step of 0.001 seconds. Clicking Go produces the integrated sine of 10 pi t signal. We can compare the performance of our discrete integrator with a continuous integrator by connecting a continuous integrator to the test signal and plotting it in the same plot block. The discrete integrator response is shown in red and the continuous integrator in blue. We see the performance is similar. It could be improved by decreasing the update time 1 value. Let's set it to 0.005 and rerun the simulation. As expected, the discrete integrator performance has improved and more closely follows that of the continuous integrator.